Hello and welcome to Risk Analytics. This is an introduction to risk analytics. We could do an entire semester class on this, but we're just going to briefly touch upon risk analytics. And my name is Hari Rajagopalan, and I'll be walking you through this module. So let's talk about what risk analytics is. We finished descriptive analytics, we finished predictive analytics, then we went to prescriptive, and now we are finally in risk analytics. So the whole point of risk analytics is a way to deal with uncertainty. And uncertainty is very difficult in decision making, and a lot of times there is the psychological aspect of facing uncertainty. Some people react with paralysis, they completely freeze, or then there's the whole paralysis by analysis, which is continuing to do research to avoid making a decision. It's very important to understand when dealing with uncertainty is that there's a chance you're wrong, because you can make the best decision with the data you have, and you don't have the data that you actually need. So you've got to take a best guess, and you could be wrong. So we're going to discuss, what is uncertainty, what is risk, and all up to this point with descriptive, predictive, prescriptive, we've assumed the information we have is correct. So when we say demand is 500 units, cost per unit is $5, we're like, that's it. We've got that, right? Of course, with demand, when we did the forecast, we did build some confidence, 95% confidence intervals. So we did get into some probabilities to say, hey, here is some confidence within which we think this is going to be between this and this. So we did have some of that, but mostly we were dealing with deterministic statements, especially in prescriptive analytics. So we made very deterministic statements, but in reality, we don't know what the demand is. We have an estimate, and it could be there or it could be off. So a lot of times when you do prescriptive analytics, you've got to be careful about taking the best answer, because it is the best answer given that all your data is correct. All right. So the other example, we hope that cost is on average $5, but it could be more, it could be less. And so this is called probabilistic or stochastic. And this is the world we live in. So a lot of times we take decisions when what we want is prompt and authoritative decisions by people. And we often judge these decisions as good or bad after the outcome is known. But in reality, the decisions are neither good nor bad after the outcome. Success can happen because the world is probabilistic. You could make a very, very good decision and actually end up in failure. You got to differentiate between the process and the outcome. What was the information they knew when they took the decision, not after we knew what the outcome was? Okay, so this is very important to understand as a manager and a decision maker. So we're going to talk a little bit about simulation and how we are going to handle uncertainty and risk with spreadsheets. So in many spreadsheets, the value for one or more cells representing the independent variable is unknown or uncertain. As a result, there is uncertainty about the value of the dependent variable, right? So if you don't know what your demand is, if you don't know what your cost is, you have only estimates, then your profit will be uncertain. So here is this function, and all the x1, x2, x3 are all uncertain, then y will be uncertain. And so simulation can be used to analyze these kind of models. So let's talk about what a random variable is. A random variable is any variable whose value cannot be predicted with a set certainty. Many input cells in the spreadsheet are actually random variables. For example, future cost of raw materials, future interest rate, number of employees in a firm, expected product demand. And decisions are made on the basis of uncertain information involve a certain amount of risk. And the risk is essentially a potential for loss. So we have to analyze risk, right? So plugging in expected values, and when we say expected values, that's mean average for the uncertain cells, tells us nothing about the variability of performance measure we base decisions on. So we saw this when we did when we did mean and dispersion, measures of dispersion and measures of central tendency, right? Just putting an average doesn't help us. You need to kind of have some idea about the spread. So suppose a $1,000 investment is supposed to return $10,000 in 2 years. Would you invest if the outcome ranges from 9,000 to 11,000, narrower, but you're more sure of getting some profit, or outcomes ranges from minus 30,000 to 50,000? So the first investment, safer, low returns. Second investment, riskier, high returns. So 2 years, 1,000 becoming 10,000. This is both of this, the average of both of this is 10,000, right? Some of you might say, hey, I'll just take the safer return because here, this is actually increasing 10 times in 2 years, which is a really great return, right? And you might not want to take this risk. Some of you might take a risk. So it all depends upon your propensity to take risk. And alternatives with the same expected value may involve different levels of risk. So there are methods of analyzing risk analysis. And the first one, which a lot of us do, is best case, worst case analysis. And I'll give you an example of best case, worst case analysis. There is what if analysis. And then the better version, which is simulation. And we'll talk about each one. This is what we're going to focus on, but we'll talk about these two. So in best case, worst case analysis, once you build a model, you plug in the most optimistic values for each uncertain cell. That's the best case. Worst case, you plug in the most pessimistic value. And this is easy to do, but it tells us nothing about the distribution of possible outcomes within the best and worst case limit. So let's take an example. Here is, let's say this is the worst case and this is the best case, and this particular variable is normally distributed. That's nice, but we don't know anything about it. So your best case, worst case could be something like this, right? Very often in my undergraduate stats class looks like this, where a whole chunk of students do well and a whole chunk of students do a bad job. So I have an average, but nobody has the average grade. So if average could be 70%, but I have a whole bunch of people at 80, 90, and a whole bunch of people at 50 and 40, and then average comes to 70, it's not a nice normal curve at all. You could get something like this, which is skewed to the left. You could get something like this, which is skewed to the right. So if you just have best case and worst case, you don't know what's happening in the middle, right? So the next step, we kind of look at it and say, well, let's not do just two values. Let's do a what if analysis. We plug in a whole bunch of different values and see what happens. And this is easy to do in spreadsheets. There's something called a scenario manager in a spreadsheet, and you can easily do this. The problem with this approach is that the values may be chosen in a biased way. It's not completely random. And then if you want to generate hundreds and thousands of scenarios, you need to generate a representative sample, and it does not supply tangible evidence. Facts and figures need to justify decisions to management. And you really have, maybe you have 5, 6, 7 scenarios, but you can't use any statistical analysis on this because you are not randomly choosing the values, right? So simulation is essentially an automation of what if analysis. And you're choosing these values in an unbiased random way. So you're sampling randomly now. So you're taking random samples for these cells. And when you start taking random samples for these cells, then statistics and all the confidence intervals and the z-scores, all the stuff you learn, start applying. Because remember, central limit theorem, when you're randomly sampling people, when you're randomly sampling your data, and you even from non-normally distributed data sets, it becomes the sample values, the sample means or sample proportions or whatever it is, the sample statistic becomes normally distributed. So a computer can generate hundreds of thousands of scenarios, and we can analyze the results of these scenarios to better understand the behavior of performance. And then we can make solid decisions. So to properly assess the risk inherent in a model, we need to use simulation because that actually gives us a good idea. And simulation is a 4-step process. You identify the uncertain cells in the model. First, you have the model, then you identify the uncertain cells. implement appropriate random number generators. We'll talk about this for each uncertain cell. Replicate the model so many number of times, and record the bottom line performance measure, and then analyze the sample values collected on the performance measure. So what is this risk solver platform? It's a spreadsheet add-in which all of you have installed in your computer. The student version is available for $25, and it provides dialogues and functions. You don't have to remember your formulas, generate random numbers, commands for running simulations. It does graphical and statistical summaries, and you can get more information right here. So all of you should have this in your Excel file. So let's talk about random number generators. So a random number generator is a mathematical function that randomly returns a value, right, from a particular probability distribution. So if you want normal distribution, it generates numbers from that normal distribution. If you want a Poisson distribution, it generates numbers from that. And we can implement random number generators for uncertain cells to allow us sample from the distribution of values expected for different cells. So let's take an example. Excel has its own built-in random number generator, and that's called RAND. RAND with 2 brackets, nothing in between. And this uniformly returns numbers between 0 and 0.9999, right? So between 0 to 1. And we can simulate an act of tossing a fair coin if we want to here. If 1 represents heads and 2 represents tails, we can use this random number generator. It's 50%, right? So we use our RAND. If it's 0.5, we say it's 1, which is heads. Otherwise, it's 2. And I'll show you how to do this in Excel. So let's just take the random number generator in Excel. So you notice that this will actually generate numbers. And if you press F9 and let's go to formulas and say calculation automatically. Say calculate. Every time you calculate a sheet, it'll generate a new number between 0 and 1, 0 and 0.999, and it's uniformly distributed, right? Every value has equal chance of being generated. So if I want to do a coin toss, so I can do if RAND is less than 0.5, I can just say heads if I want to, and then I can say tails if it's not. So here we go, we have heads. Let's do this coin toss. Let's go ahead and do it 30 times, right? And here we go. We've done 30 times. Let us go ahead and calculate how many heads and how many tails we have. So I'm going to use Countif, and I'm going to select this range. I'm going to put an F4, and the criteria is it's heads, so I'm going to select heads. And since I have heads, the table is absolute. I can just copy this down. And so now when I calculate the sheet, you can see that the heads and tails change every time, right? So it doesn't always come 15-15 just because it's 50% chance. Remember here, sometimes it's 20-10, right? And so here we have a simulated coin toss using the RAND function. Let's take another example of simulating a roll of a die. So we want values of 1, 2, 3, 4, 5, 6 to occur randomly with equal probability of occurrence. So that's uniform. So then we can use a random number generator. This is the function we're using. It's 6. So we are taking RAND, we are multiplying 6 times that, right? So you get anywhere from 0 to 5.999, right? When you're multiplying 0.999, so you'll get 5.999. And so what we want to do is take the integer value. And if you take the integer value, what happens is that when you have 0.4 or 0.5, it'll give you 0, right? But we don't want 0. We want from 1 to 6. Here, this one here will give you 0 to 5. And so you add a +1 to it, and that will create your random number generator, right? So when it falls, when the number gets between 0 to 0.99, you'll get 1, 1 to 1.99, you'll get 2, and so on. Go ahead, I'm not going to show this to you in Excel. Go ahead and try this out in Excel. Okay, we will now move on to the risk solver platform. Now we are not going to use the RAND generator, though you can use it to do a lot of simulation if you don't have the risk solver software. But the risk solver software makes it a lot easier because now we don't have to learn all the formulas and we don't have to work through all the formulas. So we're going to generate random numbers with the risk solver platform, and risk solver uses the PSI function. So anything with starting with the PSI function is the risk solver platform, and it's used in formulas just like any other Excel function. But you need to have, for it to be read, you need to have this risk solver installed and working, the license working. So the distribution gallery, you can actually use a function and do it, or you can use something called the distribution gallery, which has the graphic depictions of random number generator. And we'll go to Excel and I'll talk about it. So some of the risk random number generators are, we have binomial, and that's given by the function binomial, PSI binomial. You'll need number of trials. You need to give the number of trials and probability of success there. Poisson. Poisson will ask you for the average number of events given in some time. Continuous uniform, which will ask for minimum and maximum, and it'll return decimal values. Discrete uniform, you can use PSI int uniform, min and max values, and this will give just the integer numbers. Exponential, PSI exponential wants the average time per event usually. Triangular wants the min, most likely, and maximum numbers. Most likely is usually the mode. Normal needs mean and standard deviation. You could have truncated normal where you have mean, standard deviation, and then you'll put PSI truncate with min and max, in which case you kind of, sometimes, when you're looking at, let's say, profit, or you say revenue is normally, or price of a product is normally distributed, and you are getting negative values because of a large standard deviation, you can say the PSI min, the truncated to 0. You also have custom discrete. So if you have some tables with some weights saying here are the 5 different values and here are the probabilities, remember these weights should add up to 1, you can use this PSI discrete function. And there are many, many more others. We'll be focusing on these for this particular class. So essentially the way we can access them is we can click this FX here and get the insert function, and then select a PSI distribution and a PSI function from there. Or and I'll go to Excel in a minute. Or here is an example of the different distributions that you're looking at, and then you can also, these are discrete distributions. So let's go to Excel and let's look at the function and then the gallery right now. Here we are back in Excel. So you can get your PSI functions. So here is a whole bunch, PSI distribution. Here are the different distributions. You can get, there's a whole chunk of them. Or you can go here and look at the distribution gallery here. Here are some of the common ones. We will be looking at normal, exponential, triangular, and uniform. In the more advanced ones, we're not going to look at any of these. We are not going to do any of the, we're going to look at integer uniform, binomial, Poisson. When you do financial investments, logarithmic might actually come into play. And then we will use PSI discrete. So we probably aren't going to use too many, and then there's the discrete uniform here. But apart from that, we are not going to use too many of them. But here are the distributions available to you. All right, so let's talk about some of the discrete distributions. We talked about binomial. And you see that binomial has number of trials and probability of success. And you can see how it looks like. So we have the binomial distribution, and as you can see, as the probability of success increases from 0.2 to 0.5 to 0.8, you see the probability of getting, 1, 2, 3. You can see here, this is 30 probability of getting 2 successes out of 10 is about 30%, whereas here it kind of goes more to the middle. And then of course, if you have 50% chance and you have 10, then 5 would actually be the highest. And you can see that now it's shifting to the right. Similarly, if you have PSI discrete, here are the number of the values and the weights. This is PSI discrete uniform, 20, 21, 22, 23. You can just give them the minimum and maximum value, and that should be enough. The Poisson needs an average rate, PSI Poisson, and as Poisson values become larger and larger, the values become closer to, looks more normal. These are discrete distributions. Here is examples of continuous distributions. Normal distribution needs mean and standard deviation. Here is how the PSI truncate. We will not be doing the chi-square distribution, but exponential. Usually it's average time per event. Like if you're getting queuing, a number of people coming in, they're coming in every 5 seconds, 10 seconds, that you use exponential usually. Triangular has minimum, most likely maximum. A lot of times in project management, you can use triangular distribution, and here is the uniform distribution. So when we talk about discrete and random variables, discrete random variable may assume one of a fixed set of integer values. So number of defective tires on a car can be 0, 1, 2, 3, or 4. Continuous random variable may be one of infinite number of values in a specific range. So amount of gasoline could be between 0 gallons to a maximum capacity with even smaller values, with decimal values in between. So once we have figured out what our model is, we put these random variables in. We also need to figure out what are dependent variables. What is it that we're trying to forecast? It could be the profit, total cost, and we always add this PSI output to tell Excel that this is the dependent variable. So let's example, we are trying to figure out total profit, revenue minus cost, and then we've got to add PSI output to it so that we can analyze total profit. So all the stochastic information will be based on total profit then. So how do we analyze the stochastic model? We use statistics. So we find out average profit, median mode. We can do maximum, minimum value, percentiles, measures of dispersion, standard deviation. Then because we're sampling, we can have standard error, build confidence. We can also find the probability of getting some value. And many more statistics are there. So for these statistics, again, we have PSI functions. PSI max will give you the max. When PSI max off that output cell we talked about will give you PSI max. PSI min will give you that. Mean gives you, and then PSI standard deviation, PSI percentile. And we'll go through this. PSI target returns the probability of reaching a target value or less than a target value. Mean CI gives you the confidence interval, and then there are so many more of them. Okay, and we'll work through them. So, uncertainty of sampling. So let's look at what this uncertainty in sampling is. Remember that we are sampling. It could be 1,000, it could be million sample number, the sample size. Now for your student version, 1,000 is probably the maximum it'll allow. I mean, they can allow more, but let's keep it at 1,000. But we are taking 1,000 values from some data distribution. Let's say we say demand is normally distributed to be 5,000 units, and then standard deviation is 1,000 units. So then you're going to generate 1,000 such values. That's your sample size, right? But it's still a sample. So when we repeat the simulation and obtain a new sample for the same size, will the statistical results be the same? The answer is no. And I'm being very specific here because a lot of times, the two of you, if two people submit the same model and run this, do it properly,
you should not have the same answer. It's highly unlikely that you have the same answer. And if you do, there is a problem, right? So, I mean, there's a problem. There will definitely be a suspicion whether you collaborated, used the same file, just copied the file and submitted. So you should not have the same answer. So as sample size, the number of replications increase, the sample statistics converge to the true population value, as you learned in the first part of descriptive statistics. We can also construct confidence intervals for these statistics. We also use simulation to describe like the behavior distribution of some bottom line performance measures when one or more input variables are uncertain. And often input variables are under decision makers' control. So these are the decision variables, right? How much should you produce, right? And you've done this with prescriptive analytics. So now we can use simulation to assist find some optimal values, but because we don't know exactly what the values are, these are all on average, they would be the best. And I'll talk a little bit more about optimization using simulation. So we finished kind of an introduction. Next lecture, we'll go into the details and get into Excel and look at example problems.